Okay, I think we'll crack on with the last bit now and finish off with novel materials. So this is the catch-all bit for anything that wouldn't fit into the previous three sections, basically. So we'll start off with, I'm not sure it counts as a novel material anymore because everyone's talking about graphene, everyone's analysing graphene, everyone's trying to determine new uses for graphene. I was invited by the National Physical Laboratory, who we collaborated with on this publication, which describes the experiments I'm going to talk about in a moment in a bit more detail, to the Houses of Parliament in London for the opening of the National Graphene Centre. And on the side of, on a table in the committee room where they were having the reception, they had a range of products to justify why you needed a metrology institute to get involved with analysing graphene. And there was graphene underwear, there was graphene health supplements, there were all sorts of things. I mean, you definitely don't want to be eating graphene, particularly. It's not... and so they were saying you need to be able to analyse and have a standard for determining whether something actually has any useful graphene in it whatsoever to justify calling it that, rather than it just being marketing. So we worked with the National Physical Laboratory in the UK on looking at how, when you're preparing graphene samples to use in devices, how you can determine, once they've been transferred from the growth medium onto a medium you're going to actually use to prepare the device, how you know that that's been successful and you've got a clean surface. And to do that, we're using XPS, obviously, to check the chemical state of the material. We're using UPS to check the valence information, as we just saw with the PFO. And we're also going to use Raman spectroscopy to understand the quality of the graphene film that we have at the surface. So first off, we have a look at the XPS. So this is the carbon spectrum from the actual sample. And it should look like this spectrum over here. So these two are reference spectra from our XPS Knowledge View and the XPS-Simplified.com website. And you see this asymmetric structure. This is because a graphene and graphite, which has a similar structure, is conductive. And the more metallic character you have with a conduction band and conduction electrons, the more asymmetry you get in the peak. As they become oxidized and less conductive, you lose this asymmetry and you get something that looks much more like this with the more symmetrical peaks. So our graphene spectrum should look like this, but we're seeing a peak here which is unexpected chemistry. And the way this sample is prepared is it's grown on a copper substrate, then it's transferred onto polymethyl methacrylate, so PMMA, and then it's transferred from that PMMA onto the silicon wafer to prepare the device. And it's probably some of the polymer that's left on the surface of the material. So if we have a look with the Raman spectrometer, we can see the characteristic peaks of both the silicon substrate, so these three peaks here, but also the ones for the graphene. So the G and the D bands are the ones I'm going to concentrate on. The G band is representative of the actual quality of the film. So if it's good quality, you just see a G band and you don't see a D band. The D band is indicative of any defects you might have in that hexagon graphene structure. So what we can do then is clean the sample using the Magsis cluster source. If we go any higher than the lowest beam energy and go to a smaller cluster than 2,000 atoms, you damage the graphene. It just breaks it apart. You have to be really, really gentle with this stuff to clean it up. And then we remove the contamination. So this is the surface, and then as we etch away, this peak disappears until we get something that just looks like that asymmetric tail we'd expect on the graphene. Whoops. And over on this side, we're measuring something we call the D parameter. And this is just a measure of the sp2, sp3 carbon chemistry. So sp3 is diamond, basically. sp2 is graphene, graphite. So the more sp2 we have, the more we have our graphene surface. That's what we want. it's quite a simple measure to do. We just measure the carbon KLL Auger feature, which is quite a bit higher in binding energy than the core level, and differentiate it, and the software automatically does the measurement to see. So we can just plot this out from our depth profile. This is indicative of the contamination at the surface, and then as we clean it, we get towards 21, 22 EV value, which is what we would expect for graphene. So we're cleaning it, and from this measure, we can see that we're getting to graphene. However, we don't know from XPS whether the surface is actually staying stable or not, whether we're damaging it, because we're firing ions, even cluster ions, at the surface. Is that damaging the graphene material? So we'll track that by checking the ratio of our G and D bands. And if we do that, and that's this dotted line here, which is plotted on this axis, the ratio of G to D stays exactly the same. So the cluster ion beam isn't damaging the graphene film. We're maintaining the ratio of those peaks. We're not damaging the hexagonal structure of those carbon atoms in the graphene. And so we know that we're keeping it stable and without causing any damage in the surface. So that's pretty cool, and the guys at MPL have now started working on this as a process to actually recommend for production. Cluster beams were originally developed for cleaning silicon wafers. So you have your large 12-inch wafer, and they use 10,000 atom or 20,000 atom argon clusters to just polish the surface of the wafer after doing the sort of hydrogen fluoride etching on the wafer to clean the surface. You need something to then polish that surface to get it nice and smooth, ready to do the deposition of the chip material. And that's why the ion sources, cluster ion sources, were originally developed. So having them come sort of full circle for when you're developing graphene devices and cleaning up the graphene before you start modifying to make them slightly less conductive and more useful for doing electronics with is quite a nice sort of, the circle is complete. Okay, we're back to CISA now for the next 2D material example. So we move on from graphene to another of the analogues of graphene, and that's molybdenum disulfide. And this is the workflow that James was showing this morning, if you remember, with the polypropylene and the carbon and the copper nanoparticles. So we mount the samples on a special sample holder which has fiducial marks to be able to reference the positions between the instruments, and then we can do XPS, and then we can do SEM, and then using the MAP software we just correlate the data sets together to be able to understand them. So this was a commercially bought sample, so we wanted some of these 2D materials, so we bought what was supposed to be a wafer covered with molybdenum disulfide, just a single atomic layer of MOS2 across the surface. And what we found when we analysed it was it's really, really patchy. So this is the molybdenum snap map, and where it's light is where we've got a strong molybdenum signal. Where it's dark, we've got a weak molybdenum signal. And it's never going to be super strong because it's only one atomic layer, but it's really, really patchy. And in some areas, we've got no molybdenum at all. So we thought about asking for our money back, and then we thought about maybe trying to use this as a nice example to use in seminars like this one. So next step is to do a bit of Raman on it. And again, like graphene, molybdenum disulfide is a very good Raman scatterer. And actually, the interesting thing is the separation of the two peaks we get due to molybdenum disulfide is determined by the number of layers we have in the structure. So the fewer layers we have, the smaller the separation between these two peaks is. So this is a bulk reference of MOS2, and that has a separation of about 25 wave numbers. And at 0.1 here, where we have a nice strong molybdenum disulfide signal on our sample, we just have a separation of 18 wave numbers. So that suggests that we've got something close to a single atomic layer, at least at that point. So if we have a look at another area on the sample, so this is our original area here in red, and this is another area down here, much more signal down here. We can see much more, but we see a larger separation in the Raman spectra for the separation of those two peaks. So we've gone from 18 wave numbers here to nearly 20 wave numbers down here. And if we look in the XPS data, so this is a sulfur peak, this is our molybdenum disulfide in this chemical state, but there's also another doublet here, which is molybdenum oxide, and it's quite weak in this area, and it's a bit stronger here. So we're seeing some oxidation of the molybdenum at this point as well. But at that point, that's all we can really tell from the XPS, and so we have to take the samples out of the XPS system. These are Robin's hands, one of the members of my team, who's very good at doing this kind of thing and holding a steady cam at the same time. And he takes the sample off the Nexa sample holder. This is going onto the sample holder for our Axia system. It's just a special adapter, so we don't have to unmount the samples. And then we can pop it into the microscope. So this is the lab in the UK where we spend our days. Pop it into the instruments. I say very good at moving samples around and holding the Steadicam. And then we can pump this down. And so up in these corners here, these are the fiducial marks on the sample holder. This is the data we've imported from the XPS, and this is now the image from the NavCam in the electron microscope. And what we can do now, it's live in the microscope, and we want to now just correlate the images so that we know that the XPS data and the SEM data are being collected from the same position. So it's going to go around these fiducial marks and find them. So it's found the first one. It's moving the stage to the second one, collects the next one. Over here, that goes green to say, yep, I recognize that mark is what I'm expecting to see. It's doing the third one, goes green again, and then it moves down to the final mark over here. And once it's found those, it will use those to now match the NavCam image and the then the microscope stage movements to our data that we've exported from the XPS system. So we've now got that, and now we can see where we collected our XPS data from. So there's one point here, and there's one point down here. This isn't, I will say for this video, it's not exactly the same as the time when I actually did the data that we're showing. This is just for illustration. So it's just going to show some very quick tile set collection here. Just to give you an idea of how this works. So it's going to be slightly speeded up just to collect these quite low resolution images, but you will see the difference between the two areas on the sample before we can see some higher resolution ones. So you can see it's quite bright up on this one. It looks a little bit darker down here. If we zoom in, what we can see is these little kind of black dots you can see around here, and there's fewer of them up here. We can have a look at the composition here and see, how much molybdenum is at this point, because this is our X-ray analysis here with the XPS. It's much, much larger than the resolution we can get with the SEM, so we're able to, get a real idea of what's happening under that X-ray spot. And here you can see a lot more of these features in this image, so you can see that there's a much denser array of these molybdenum features down here at this point. And if we look at even higher resolution, we can see one that I should have bought a lottery ticket the day that I did this experiment, because what are the chances of me actually dropping that spot exactly onto, and I swear to God, this is exactly how it was. I didn't move it. So this is the low resolution area. So this is up here at this point, and we can see we've got all these little triangular features, and these are the molybdenum disulfide crystals. So we've got them across the surface here. Down in the region where we've got much more, we've got them overlapping. We've got lots and lots of them here on the sample. And so that's why we can see that greater separation of those Raman features, because we've got more than a single layer at this point. And so we wouldn't have really been able to understand that properly without having the combination of the electron microscopy and the XPS and the Raman information. So having them all together gives us the more complete picture. Now, what you might be thinking to yourself is, okay, you had it in the electron microscope. I'm getting all these lovely high-resolution images. Why didn't you just do EDS on it? And you could have found out what it was and understood what was going on. And this is the EDS from across the sample, coloured in using the Chemi-SEM on the axis. So that is always collecting EDS data while you're acquiring it. So you can just switch it on and it colours in the image for you, which is really kind of cool. And the thing is, these features are just too thin. So, harking all the way back to James first thing this morning, we look straight through them. And so we just see the silicon and the oxygen from the silicon oxide wafer, and we don't see any trace of the molybdenum or the sulfur. We just look straight through it. So you do need both techniques to be able to do it. Yep.
So this works if your sample is conducted well on an insulator. How will that be? Sometimes you have to.
Well, if you remember back to James's example this morning with the polypropylene fibers, that's an insulating sample, and so we use low vacuum mode on the SEM, which the way it works on the Axia is that you use some water vapor and effectively use that like the charge compensation system in the XPS. So it ionizes. You are able to then mop up the excess charge that you're putting on the surface. Because, you're quite right. We don't want to gold coat samples if we're going to do XPS on them. We don't want to carbon coat them. The usual way that you would make insulating samples conductive for doing SEM on is exactly what you wouldn't want to do if you want to do surface analysis on them, because putting a carbon coating down means you'll just detect carbon in the XPS. Gold coating, just detect gold. So you have to use the low vacuum mode of the SEM. So you do need an environmental SEM if you're going to look at insulating samples. Yeah, that's a good point, Dan. So you can also, on instruments that don't have the low vacuum approach, you can use beam deceleration. So you can run at a low voltage and then actually bias the stage. So you slow the electron beam down so that you can image samples there as well. So, certainly for looking at insulators, the way that microscopy technology has moved on over the past sort of decade or so has been a real help, particularly if you want to correlate your data with a surface analysis system. Last 2D material, boron nitride. And so again, we're looking at something which is an analog of graphene. But in this case, boron and nitrogen rather than carbon. It's an electrical insulator, but it's got very high thermal conductivity. And the idea that the people who were preparing the sample had was they wanted to use it for an anti-corrosion coating. So they wanted to coat the surface of a copper film with boron nitride to prevent oxidation occurring. Unfortunately, they weren't very good at preparing the boron nitride film, but it did make a really great sample for showing the way that you can do this workflow of XPS and Raman. So this is the sample over here on this side. This copper film should have had a continuous layer of boron nitride over it, but actually this red area here in this nitrogen image is the only part where there's actually any boron nitride. The green is all this organic nitrogen component, which is just the precursor that hasn't reacted. So it's only been very partially successful in terms of synthesizing it. But the question is it the right form of boron nitride? Is it cubic or is it hexagonal? We want the hexagonal form to be able to say that it is at least a 2D material, and they just need to refine their synthesis process. So we've got the snap map, and then we can choose analysis points. So one on the area where the nitride is, one on the area where the nitride isn't. In the area where there isn't any nitride, we don't see any boron. We only see boron where the nitride was detected. So we've got a pretty good idea now that we've got boron nitride there. And we can confirm it by checking the high resolution scans, and we see the intensity for boron at the nitride peak energy. There's a little bit of oxidation as well, so we see a little bit of boron oxynitride. And again, in the nitrogen signal, we see a peak for nitride, and a peak for oxynitride as well. And then we can do Raman spectroscopy at the same point as well. If it was cubic boron nitride, so if it wasn't the 2D form, we'd see a peak here at just above 1300 wave numbers, but we see the peak here at 1366, which is characteristic of hexagonal boron nitride. So we are at least getting a very small amount of the right material, and it's just a question now of refining the synthesis process to make sure that it now covers the surface. Unfortunately, under here, we didn't see any difference in the oxidation of the copper compared with outside this area, but it was such a small amount, I'd be very surprised if it was actually successfully forming a cover of the material. Okay, so moving on from 2D materials to more three-dimensional complex ones. So lanthanum, strontium, iron, cobalt oxide, a double perovskite material with hopefully applications for solar photovoltaic materials. What we want to do here is check the chemistry as usual, but then look and see whether the surface is the combination of elements that we expect using ISS, and also look at the band gap using reals. So first step, again, as usual, collect a survey scan and see whether everything we expect to see is present. And so we can see the iron, strontium, lanthanum, cobalt. So yes, it looks like so far we're seeing everything we'd expect to see at the surface. And if we look at the lanthanum chemistry, again, this is, we should only have 2 peaks for a 3D transition, but due to quantum effect by the number of electrons that lanthanum has, we see the doublet split into a multiplet, and so we have 2 peaks for each component of the doublet. But the splitting of them is quite diagnostic of the chemical state, so the distance between these 2 peaks, depending on the type of compound you have, gives you a different value. And so here we're looking at something that's got sort of lanthanum 5 plus, that is 5 plus, I'll read it from here. Lanthanum 3 plus oxidation state. And then we could do the ISS, because the XPS is telling us that sort of quantification of the 20 to 30 atomic layers of the surface. But what we really want to know is what the outer layer is of the sample. And if we look at it before we've cleaned it with the ion source, so this is the as received. So it's quite interesting. We see a little bit of argon in the surface. This is from the production process as they were depositing the material into the sample. So we see a very strong strontium signal and oxygen. And so the surface is strontium rich. If we compare that with the XPS composition, we'd say that the strontium was one of the lower components in the material, but it's actually the strongest one at the outermost surface. Remember, this is the outermost atomic layer of the material. Then after we clean it, we can see the other components. So we start to see the lanthanum, iron and cobalt overlap, unfortunately. So we just see 1 peak there, and then the strontium peak and the oxygen as we have an oxide. But there, the ISS is giving us some quite useful information in being able to understand exactly what the outer surface termination is of this particular material. And then finally, we can check the band gap. So have a look at the band gap here, and again, just reals. So you can see the intensity of the elastically scattered peak compared with the background that we're actually using to measure. So this is only about 10% of the scattered electrons, and we're able to measure the band gap in exactly the same way as before. So this is the actual tool in the software for doing it, and once you open it, it just automatically does the calculation and gives you the band gap value for the material, in this case 6.12. Now that's quite large for a photovoltaic material. Usually you want things for using for these kinds of applications to have probably half the band gap there. So the next step for the company making this material is to then try and optimize it to bring the band gap down and make changes to the stoichiometry to adjust that, or maybe dope it with something to change that absorption coefficient. Another one is methyl ammonium lead iodide, and that's, again, same kind of process to understand this. So determine the surface chemistry, a lot of carbon present here because it's got the methyl component. Then we've got iodine and lead. And again, check the chemical state information. So we're expecting carbon-carbon and carbon-nitrogen. But what is interesting actually with the nature of this particular material is that the nitrogen is in a slightly different chemical state because of the sort of electronic properties of the nitrogen within this particular structure. And so we'd expect the peak to be about here, but because it's actually in a charged state, we see it at slightly higher binding energy. Then we can use, and in this case we're looking at the valence band using XPS rather than UPS, but we're doing exactly the same thing as we saw in the UPS data earlier on with the PFO sample, and we're just measuring the valence band offset, so the onset of photo emission, and determining where that is to measure the ionization potential ultimately. So using that, and we have our measurement of the cutoff at one end, so we can measure the not the work function, in this case the ionization potential, and use that to calculate the value using these two values, knowing the Fermi level, so this is on gold, to get the work function here, and then using the position of the Fermi level, our highest occupied state, and the cutoff, we can then measure the ionization potential of 5.4 eV. So again, we're not just determining the chemistry using XPS, we're able to get further information about the electronic properties of the material as well. And there, just to get the schematic energy diagram there. So by measuring where that valence band maximum is and knowing the position of the vacuum level, we can then calculate the ionization potential and the work function of the material. And the last sort of set of novel materials are ones that, particularly the way, I don't know how they are over here, but the gas prices in the UK are absolutely astronomical. You'd have a heart attack, I think, if you tried to fill up a car at where we are. And it seems quite cheap, actually, when I come over here. But it is looking at lithium-ion batteries. And so we have our anode material, which at the moment typically is graphite, our cathode, which is usually some kind of oxide that's able to intercalate the lithium ions, and then electrolytes. We could be certainly now what we're looking at moving from liquid electrolytes, this is exceptionally good news for XPS because don't really like the fluorinated liquids that they use for electrolytes at the moment, but moving to solid state ones like Lipon is much better for XPS analysis. And also if you've got solid state lithium-ion batteries, you can put much more energy into them. So the energy density and hopefully then the range of your car will be a lot larger if you've got a solid-state battery rather than one with a liquid cell. So lithium materials are very air sensitive, and so we need to actually get them into the system without exposing them to air. So this is actually from the initial trials of this device over here, which is the vacuum transfer module, or VTM. So you load the samples in your inert atmosphere glove box. So here, this is actually from the day that we tried it out for the first time. We went to the National Transport Research Lab at Oak Ridge in Tennessee. We put in a piece of lithium and a couple of bits of battery material. And this is the same type of sample that we've just put into a little plastic bag and transported from the glove box at the Transport Research Lab through to the XPS system, which is in the main part of Oak Ridge. And so it was about a 30-minute drive, and we were able to keep the lithium metallic during that process, whereas the lithium metal we had just exposed to air goes this dark color with the formation of particularly lithium carbonate really on the surface. So the vacuum transfer module really useful for moving samples into the system from the glove box without exposing them to air, and that's what we need to be able to look at lithium-ion battery materials. So here's just looking at a 2 cathode samples, one not used, one used. And one of the nice things about XPS, it's one of the few techniques that's able to measure lithium relatively easily. It's got a weak signal, but as Manish showed this morning with the lithium fluoride powder, if we can access the material, we can measure lithium, which is quite tricky to do with other techniques like EDS. So here, between the pristine sample and the cycled sample, we can see there's more lithium at the surface in the pristine sample. After cycling, we're seeing less lithium, and that's partly due to the formation of this SEI or layer, which is kind of what reduces the capacity of the battery because it limits the ability of lithium to transport from the electrode through to the other electrode. And so looking at those SEI layers is one of the things that XPS is used for as well, quite commonly on these types of materials. For the LiPon material in the electrolyte area, we were looking at a depth profile here to see how consistent the material was. And we tried doing it with a monatomic argon profile, and we found this increase in the lithium signal here at the surface when we got to the silicon. And we thought, oh, that's interesting. I wonder why that's happening. And then we discovered that that was actually because of the monatomic argon beam. And so the ion beam was pushing the lithium through the sample as we were etching it. If we use the cluster source and profile it with quite an energetic cluster, so 8 keV and only 75 atoms, we're able to mill through the material quite easily, but we don't see that spike in the lithium concentration. And so we're actually measuring the film as it is. You can also see the actual amount of lithium we measured throughout. It's not a huge difference, but we're just below 35% along here, and we're exactly on 35% here. So that small variation in the lithium concentration is that lithium pushing through the film as we sputter with the monatomic ion and coming to the surface here. You see the same kind of thing with sodium as well and other alkali metals. They're quite mobile and ion bombardment. So if you're looking at samples like glass, you do have to be quite careful with milling through them. And then the last material from the battery collection is lithium cobalt oxide. We wanted to just look at how this looks with XPS and Raman on a couple of different areas on the sample that appeared slightly different. So again, if we do XPS and get our survey scan to identify the elements, we can see a small amount of lithium, we can see the carbon, oxygen, fluorine. Fluorine generally from the binder that's holding the material together. So when they turn it into an electrode, typically they use something like PVF or PVDF to hold all the material together. So you tend to see fluorine all over lithium-ion battery electrodes. If we look with the Raman, so coincident, this is using the 785 laser, so heading towards the infrared, and we can see 2 peaks from the lithium cobalt oxide, and then a load of sort of junk basically from the binder material that's there holding the sample together. Comparing with a couple of different positions, though, we can see that there is a bit of variation. So at point 1, lots of fluorine coating. Not so much fluorine here, and we can see variations in the amounts of cobalt and what else? Silicon present in these different points. And we thought it might be quite interesting to compare those. So again, we can see if we look at the cobalt chemistry, we can see that there's actually a variation in the oxidation state between the 2 points. So at point 1, we've got mostly cobalt 3+. Point 2 is mostly cobalt 2+, and that's really indicated by this satellite. You can see there's not a big difference in the peak position. It's the presence of these satellite features, which are, particularly for transition metals, as the oxidation state changes, you tend to see other satellite features appear and disappear, which are quite diagnostic for understanding the surface chemistry. And we could clean it up using the cluster source, and see whether that actually changes the chemistry we're seeing, looking really down for the lithium down here. And so we can see lithium cobalt oxide in point 2 after sputtering and point 1 as received. And in the as received point 2, we're seeing quite a bit of lithium fluoride present there as well. And in the Raman at points 1 and 2, that organic coating again. So it looked like from the XPS spectrum, it was due to an excess of that fluorine binder. And if we compare the Raman from the 2 points, it also suggests that's the case, that this big mess of stuff here is less present in point 1 than it is in point 2. So again, it's that combination of the techniques to be able to get the full story about the material. And although I will quite happily stand here and tell you that you can do everything with an XPS instrument, and XPS is everything you need, actually you do sometimes need to actually use a few other techniques to completely understand the materials you're investigating. And so that's what we can understand. Okay, so that's novel materials, and I got one more example I want to go through before I will release you back out into your lives, and we'll stop this hostage situation with surface analysis. And this is, I have to say, over the however many years I've been doing this, this is my favorite application example of all time. I don't know whether you'll agree with me or not, but I really like it. And it all came about by, we were at the Microscopy and Microanalysis Conference in Albuquerque about 12, 14 years ago, something like that. And we met a Dutch gentleman who was a professor at an institute just outside Amsterdam in the Netherlands. And he was very interested in the preservation of artworks. And he started talking to us. He was actually on his holidays. He was driving Route 66 and just decided, because he was doing microscopy, to pop into the conference on his way past, and started explaining about a particular sample he had. And we explained about XPS to him, which was completely new. And he thought this could be a good way of understanding a particular problem he had. And it was all down to the way that artworks can degrade over time. So there's a couple here. The sunflower paintings that Van Gogh did don't look exactly the same way as they did when he originally painted them. I think the paper that's referenced down here goes into great detail about how the chromium pigments that he used to actually get quite vibrant yellow colours when they were originally painted degraded over time due to the effect of UV on the pigments. And so they've gone browner and browner, and something that's taken as a bit of an indicator of the fact his mental state wasn't that brilliant at this time isn't actually the case. It was just the paint he chose meant that the colour changed of the painting. For Vermeer, the way he prepared his paints was quite interesting, that he really filtered them so the pigment particles that were in the oil medium are really fine and small, and so they don't bind together very well. And so on this painting, the sections of the pigment were actually just dropping off the canvas because they just weren't held together particularly well. And so it needed very careful restoration to make sure that they stayed adhered. So that's delamination. Photo-induced changes is this one. But there can also be chemical changes, and these can be down to how the artist prepared the canvas, or the paints he chose, or even just the atmosphere in the gallery. And so the painting we were analysing, which unfortunately I can't show a picture of for copyright reasons, unfortunately, but it's supposed to be an autumnal scene. So it's supposed to be a view of a meadow in the fall, again, over in the US. And it's over time, the meadow has gone from a green colour to being white, almost as if autumn is changing into winter. And this is the structure of the painting. So you have the canvas to start off with, and then the artist puts down what's called a ground layer. So this is just usually white paint that they use to prepare and get a smooth surface to then apply the colours they want to generate the image. And then they'll put a series of paint layers on there to get the colour they want, and ultimately that will give the appearance of the painting. So we were able to get a section from the edge of this painting from under the frame where it was still showing evidence of this process, where the surface was changing colour. So this is the back, this is the ground side, and this is the side that was exposed to the air. And what we're seeing is this kind of bubble feature at the surface, and then what's causing the change from green to white is these small crystallites that we can see in the SEM here. So this 3B area here is the thing, and this is done using the backscatter detector. So this is showing a heavier mass than the constituents of the rest of the paint. So we can do some EDS and have a look at what we've got. And so at the surface in this phase here, we've got lead, we've got arsenic, we've got chromium, typically around the turn of the century, so the beginning of the 20th century when this was painted. The paints were not complying with REACH or Roche or any of the other sort of things, and they're full of all sorts of nasty materials, chromium-6, arsenic, you name it. Phase 2 is just the epoxy that this is in. Then the green paint down here has a lot of chromium and arsenic and copper in it. The lead typically comes from the white paint, so that's something called Dutch stack white, and they make it by it's principally lead carbonate, and traditionally it was made by taking pieces of lead, putting them into containers and then leaving them surrounded by horse manure and allowing chemical reaction to occur on the surface from the gas coming off the horse manure. Very pleasant. So the green paint here, looking at the blister feature, we can see on the surface of the blister lots of lead again and arsenic in the green paint that's underneath it. So again, at the surface where we're seeing those little particles, and on the surface of this blister feature, we're seeing lots of lead. So that's giving us an indication that might be something to do with what we're seeing. So we got the sample then and put it into the XPS, and so we could just map over it just to show how it's aligned in the system. This is just a map of the epoxy around the chip. And then we could map it for the various different materials, so chromium-3, chromium-6. We found 2 different chemical states of lead, lead B and lead A. I'll come back to those in a moment, but you can see that lead B is really associated with that blister feature, which is about here. Lead A is associated with the little crystallites on the sample, and arsenic as well. We can see, again, principally in the green paint, metal oxides all over the place, and then a couple of different carbon chemical states as well, which aren't really important, but are probably some carbide or something that's forming in the sample. So it's the lead really that's of most interest. So we've isolated out the chemical states here. We've got this lead A where those little crystallites are, lead B around where that blister feature is. So let's pull out the spectra for those and compare them with some reference spectra. So we collected a range of different lead compounds. So let me get this right. PBS is the traditional Dutch stack lead white. We've got just lead carbonate from Aldrich. PB palmitate is one of these lead soap compounds, so it's an organometallic compound, and that has quite high binding energy. And then this AZPB is something similar to that as well. It's another organometallic. They're quite sensitive. They're quite sensitive to X-ray exposure as well. So the longer we kept them under the X-rays, we actually started to see reduction to lead metal occurring. So you do have to be quite careful and quite quick when you're doing these experiments. So then we compared. So we extracted the spectra from these regions and compared them with the references we'd got. And lead A compared very well with the lead carbonate from Aldrich. So that's this one for the crystallites. Lead B, where we've got that clear blister feature, compares very well with the palmitate, so the lead soap compounds, the organometallic material. And once Jaap, the Dutch scientist that we met way back in Albuquerque, saw this data, he said, "Oh, I know exactly what's happening to this painting now. I know why it's going white and the mechanism that's actually happening." We could skip through those ones. So what actually happened was that the guy was so keen on making his painting that he didn't dry the canvas properly. So there was still moisture within the canvas when you put on the ground layer here. And this is just that lead stack white. So basically lead carbonate dissolved in oil was painted over the surface of the canvas. Now that reacts with the moisture in the canvas and changes to form these soap compounds. And these soap compounds in history of art terms are very mobile, and in anyone else's terms are quite slow moving. But over 100 years, they went from the canvas all the way through these paint layers by diffusion to end up at the surface. So that bubble we saw on the surface of the painting, that was one of these bubbles of palmitates, that lead palmitate that's come up to the surface. It reacts with the air in the gallery then, and so through just interaction with the carbon dioxide in the air, or even oxygen, that forms then into small crystallites of lead carbonate. And so as these bubbles get consumed, they form these little crystallite structures, and we get this effect of these covering over the green paint and going from green to white. And so that was what was changing the surface of the painting and changing the colour from green to white. Now, the painting's in private hands, which is part of the reason why I can't say what it is exactly or something like that. It's worth a reasonable amount of money. And unfortunately, this is a completely irreversible process. But luckily, now they understand what's happening. They're able to protect the painting, keep it in an inert atmosphere, that it doesn't get worse, clean the surface so that they can prevent the build-up of these bubbles and stop the painting changing any further. So there is a kind of happy ending to the story. But yes, that's how, in a very odd occurrence, XPS can be used to preserve artworks. And that's the only time I've ever heard it being used for that. But it's still my favourite application example for XPS. And at that point, I would just like to thank you all for sticking with it through the course of the day. I hope you found it interesting and given you some understanding of the kinds of things that you can send to the team here in NIAR to run in the XPS system. And I'll be very happy to answer any questions you might have on anything we've talked about today, or anything else within the confines of surface analysis, please. So thank you very much. Yes.
Like and so on. I would anticipate work with me if you're in like the better stable, you show us how he has been degrading service. And there's always a
in most cases, you can mitigate for it's generally not a quick process. I can think of one particular type of sample where we did see it degrade very quickly, but even then we were able to, by moving the spot around on the sample and acquire, usually what we do when we're acquiring the data is we'll sit on the point and we'll acquire several scans to get good signal to noise on the data. And if in this case we couldn't do that, because if we stayed on the compound it would start to change chemically. But if we can move around and collect data at several different points, so we're limiting the exposure to the X-ray beam, and then we can just average those points together and get a representative spectrum of the data. So that's the way we can do it. There are a few things where even that won't work, and you just have to accept that it's going to change. And yes, in those cases, you might have to try something else. But generally, those types of compounds are sensitive to almost anything you try to do with it. But yes, it's a good point. You do have to be quite mindful of it. Yeah, I mean, I had, when I borrowed a Raman microscope from someone, I had a lot of fun trying to set fire to things by putting too much laser power into it, which wasn't really the point of using the instrument, but it was quite entertaining. Thanks. Yes.
so why that much help was like how I work again 60 rate then yeah. And
It will be an average over that area that we're analysing for sure. I mean, it'd be, as I said when we were looking at those particular samples, I think they need to do some more work on making them useful for solar applications, because the band gap is too big for the.
and I got what in there
For this, the accuracy is pretty good. So I'd say we're within 0.2 or 0.3 EV is probably the error on the measurement. It's we're getting such a lot of signal. There's quite good reproducibility and precision on the measurement. When the band gap gets down to those sort of optical values of around 1 or 2 eV, it becomes very difficult for us to measure using reels. It's too small, then it's too close to the scattered peak. We have to use a different technique than inverse photoemission spectroscopy to do it, which is quite difficult to do and quite difficult to explain. But that can also be used for doing it. And that's really where you have to go when you're trying to do it for those really narrow band gap materials. But yes, the accuracy's good for this. It's quite a reliable experiment for doing it. And usually it's less used for these kinds of sort of PV materials. It's usually used for semiconductors.
Yeah. You said we're small that.
A very, very small band gap, you just can't measure it. It's too close to the elastically scattered peak. So 3 and above is basically the, yeah. Any other questions? Okay, I think I'll hand back to Manish. I don't know whether you want to add anything else or.
So, if anybody wants to talk